And now it's time for our last talk of the day right here at the breakout room number 1. We have Kinshuk Bairagi. Kinshuk has spent almost 9 years in Flipkart, where he has built systems like Journey Platform, Connect, Strauger. Joining him today is Kalyan Akella. Kalyan has been engineering highly available and scalable distributed systems for close to 2 decades. They are here to talk to us about DKV FOSS Scalable, MultiDC distributed key value store, and will walk us through Flipkart's journey and knowledge of building a fast and scalable distributed KV store that supports the various data consistency, availability, and durability levels. Ladies and gentlemen, as you all know, let's get the comments coming in the box and a big virtual round of applause for these two amazing gentlemen. Let's get them up on your screens.
Myself, Kalyan, and along with Kinshuk, we both are one of the founding engineers of this project. So, next slide, please, Kinshuk. So, just to walk you guys through the motivation. So basically, Flipkart grew from a single data center, and as our functionality increased and our explosive growth, due to that explosive growth, it's been imperative for us to operate from multiple data centers. And basically, that is where we found several challenges in terms of running our stack from multiple data centers in a scalable manner, as well as keeping the data consistent across multiple DCs. So we basically ran into these use cases that we have listed here. Example, inventory reservations, which is especially a strongly consistent write use case, which needs to happen from across multiple DCs, as well as fetching the counter values for each of these inventories. That is one particular use case that we wanted to solve for. Also, there is a requirement of high durability, high levels of durability, obviously no data loss, and we want to be able to serve all of that data at really low latencies. Also, when we operate from multiple data centers, we also needed the flexibility to operate using different topologies, right? Master slave, master master, different kinds of topologies, because different application tech stacks will have varying levels of scalability requirements, varying levels of architectural requirements, which will require us to basically solve for different topologies. The other aspect is that we needed elastic scalability as well, because there are inorganic events that, growth events that can happen thanks to sales and so on and so forth. So we want to be able to basically have the tech stack, elastically scale up and scale down. So all of these are primarily requirements for our data stores to be able to operate from multiple data centers. And when we have all of these use cases, we went about exploring the outside world in terms of both the commercial as well as the open source and free offerings, in terms of what kind of offerings are out there that can meet our purposes, right? So as part of the journey, we work with CockroachDB, YogabyteDB, TIKV, etcd. We've explored several of these offerings. We made detailed analysis, and then at the end, we concluded that basically there are two main problems in terms of using any of those technologies for our use cases. First one being basically our feature set, they're not cutting it. So there are only partial set of features that are supported by most of these open source offerings or commercial offerings. Especially, for example, we needed the ability to do consistency, which is tunable. Okay, so because most of these offerings tend to give you consistency by default for all the reads, but that is not something that we want. And we can go over the reasoning a little later. But there are some of such features which are only there, and the entire feature set is not basically covered by any of these offerings. That's the primary purpose, the primary reason. And the second reason being, there are a few enterprise offerings, case in point being CockroachDB, which did support most of these requirements. But however, for the amount of data volumes that we are dealing with, we will have to basically pay quite a bit of licensing as well as operational costs, which did not make sense from a longer TCO standpoint, long-term TCO standpoint. So that was basically the premise when we started looking up. And then we happened to have come across this talk from ZippyDB, which basically almost all of our founding engineering team got inspired from. It's a proprietary software built by Facebook, and there was a talk about this on YouTube, and that basically is an inspiration for us in terms of how should we approach coming up, with an architecture for distributed databases, and especially key value stores. Just an emphasis on key value. Most of our user path front end, most of those database schemas are key value based, and so we have focused our efforts on building a key value based store and making it distributed across multiple DCs. Okay, and another aspect is that just when we began working on this problem, it almost grew out of from an experiment. Basically, we did a few experiments. One thing that we realized pretty early on in our journey is that there are actually several foundation building blocks that are already available out there, which will help us create such an offering. Basically, case in point again, our DKV stores all of the data as LSM trees on the disk, log structured merge trees, and there are mature implementations of LSM-based storage engines out there, right? For example, RocksDB or Badger, right? So we don't have to reinvent the entire wheel in terms of basically creating a storage engine from the scratch. We didn't have to do that. Another example was we needed the ability to scale up, scale down elastically, which means we needed that network abstraction as a core principle within our stack. And already there are offerings like Envoy, for example, which we could use and basically solve our problems. So the reason why I mentioned this point is because DKV is basically built out of these foundational building blocks, okay, like a storage engine, like a network abstraction, like a raft consensus, and then we brought these building blocks together and then integrated them and built the system the way we wanted it, right? So this slide basically talks about the various features that we currently support within DKV. Basically, it is a key value store, like I said earlier. Predominantly, our database schema is key value based. So keys and values are arbitrary byte arrays, and they can be manipulated through gRPC APIs. Okay, so there is always this classical conundrum between consistency versus availability in the face of network partitions. So we designed DKV from the ground up to be strongly consistent for writes. Okay, so we will never sacrifice consistency at all for single key writes for the time being. And the reason I mentioned time being is because down the line we're also thinking about strong consistency for multiple keys as well. But right now we only operated strong consistency at a single key level, strongly consistent writes, as well as tunable consistency for reads. So this is another important point for DKV because our access is not homogeneous. Okay, sometimes we will need the key values to be as latest or as strongly consistent as possible, but at some other time that same key can actually be served from a stale value, no problem, due to scale reasons. So we want to be able to exploit that design trade-off at an individual key level, and that is an important point for us. That's the tunable consistency is a core requirement for us. So that's the CP point of view. And from an AP point of view, we wanted to obviously have as high availability as it can be possible, with this kind of a stack. So we will be able to tolerate multiple node failures during writes by making use of quorums. Okay, so that is one aspect we will touch upon very deeply down the line. And secondly, we also can tolerate majority failures, okay, and continue to serve the reads with the remaining nodes. Okay, so we have that ability as well. Also, we want to be able to scale horizontally, scale any part of the stack horizontally in both the directions, right? Elasticity is an important point, like I mentioned. Plus, we want to be able to be versatile in terms of the replication topologies. Okay, so these are all the various features that we currently have, and all of this work that we've put in so far has been open sourced. It's on GitHub at that link there. Okay, Kinshuk, next slide. Thanks. So now let's talk about the design principles that underpin this DKV development. So first and foremost, early on, we made this decision where we wanted a very simple deployment scenario where we wanted a single executable, which can basically play different kinds of roles. Okay, we'll talk about those roles, what they are, but at a high level, that same executable can be a DKV master or a DKV slave or DKV discovery service, so on and so forth, but it's a single executable. Okay, so you give different command line options, and that is basically going to give you the functionality, right? And we also made sure that in our tech stack, we can add incrementally keep adding these features, okay, so that there is not any expensive sort of rollback kind of a features or in kind of evolution that we have considered. So it's all incremental, incrementally add additional features. We want to be able to elastically scale up and down the DKV cluster. That's also another design principle that we have set forth from the beginning. Also, we basically wanted to make sure that data is never at a single location, okay? Because that will obviously give rise to a single point of failure, and that is against our availability principle. So we want to make sure that the data is always replicated across nodes, and we use write-ahead log as a mechanism for achieving durability. So every change is first persisted into a val and then applied to the key space. Okay, so these are some of the foundation principles that we've adhered to when it comes to durability. Also, we also wanted to make sure that the clients are fairly higher performance, so we chose gRPC there, and we also went after network abstraction, like I briefly touched upon earlier, that we're using Envoy to be able to basically give us the ability to scale up or down the DKV cluster without needing any downtime by the applications that are using this DKV, okay, at runtime. So therefore, we went ahead with those principles. So here we talk about briefly what the key components are that make up the DKV product. So as I touched upon earlier, there are storage engines. Basically, the key space is stored on the disk as LS entries, and RocksDB and Badger currently are two known, very famous and stable storage engines based on LS entries. In fact, Badger also gives us the ability to run DKV, both disk-based, which is the default, as well as in-memory, okay? Purely in-memory kind of a use case as well, right? So that is possible. We also have another component called Nexus that is essentially a data replicator. So one of the things that we wanted to do from the outset is that being able to spread your data across multiple failure domains or multiple data centers or multiple regions, right? And we want to be able to synchronously replicate the changes to that data across these data centers in order to achieve strong consistency on writes. So we use this another open source offering called Nexus that we have basically built in-house. And that is also an open source project, by the way. And we'll talk about that in detail later on. But that is another key component that allows us to do this. Next, the DKV server. Okay, so the single executable I was talking about, the DKV server, that has basically three roles. A discovery manager, which keeps track of the current topology, the layout of the topology, okay, what masters are there, what slaves are there, what slaves are connected to which masters, so on and so forth. Second, you have the masters, which can accept, which basically do writes, but they can also accept reads depending on your consistency requirement. Okay, like I said, it is tunable consistency, so sometimes the reads can also go to master. Lastly, there are replicas, which are essentially slaves, which only handle reads. That's it. Okay, so these are the three roles. Then we also have DKV and Envoy. Basically, that's the network abstraction layer for us to be able to help the applications discover these topologies at runtime without restarts. Okay, that's the key point. Without any restarts, that layer is going to help applications detect this. Okay, and we also have DKV clients, which are essentially libraries written in Golang for now and Java. More might come in the future for applications to integrate with DKV service. Okay, next slide, please, Kinshuk. Right, so this is the system overview, like 10,000 feet view. So you have the discovery manager all the way at the top, which keeps track of the various clusters. Each of these big boxes here labeled DKV server. So that box is, essentially you can think about that as a region or a data center or an independent failure domain. Okay, so that failure domain will have a discovery client, which keeps tab, which gets its updates from discovery manager about node failures or topology changes and so on and so forth. You have a data replicator layer, which we'll talk about in detail in a minute, that takes care of the synchronous data replication between data centers or between failure domains. Then you have the storage, okay, that we just discussed about, which is RocksDB or Badger. That is the part that stores the LSM tree along with the write ahead log I mentioned for durability. Okay, and lastly, there is a API gateway that basically exposes the gRPC service for interacting with this key space. Okay, so overall, that's how this picture puts together. Now, if you focus on the right side bottom, there is another layer there. The box, there is a CDC client there. So CDC is another very important technology that we have enabled within DKV, which is nothing but change data capture. What it does is it is going to receive the stream of mutations that are happening on the masters on the user's key space, and those stream of mutations are applied onto another store, which is basically your Replicas store. Okay, and that is used for serving the reads. Okay, so CDC is another central implementation in our tech stack. So this is the overall system view, and we'll now talk about the data replicator part of it, the Nexus part of it. Right. So Nexus is essentially a synchronous replication layer for handling data replication across multiple failure domains. Okay, so it is built on top of Raft protocol. So the Raft protocol implementation also is something that we have borrowed from etcd Raft, and we made certain modifications on top of that, and we're able to integrate with that. So this Raft protocol is also yet another example of a foundational building block that was already available for us, which we can basically integrate with and achieve this kind of a sync replication across DCs. Okay, and what Nexus also gives us is it gives us the ability to replicate the data in an opaque manner. So what does it mean? So essentially, let's take Redis, for example. If you have a plain vanilla Redis, which is just sitting there, and you want to make sure that its key space is replicated across multiple data centers, how do you do that? Today, it is not trivial to do that unless you are going with Redis Enterprise or some other fancy features. Yet another way to achieve that would be through Nexus. So you basically connect Redis to Nexus, and Nexus will be able to take over those writes from Redis, distribute them into another Redis synchronously over the Raft protocol, and individual Redis instances will be committing that write. Okay, so the Nexus will keep track. That's the bookkeeping layer on top. So currently, there are integrations available with Redis as well as MySQL, by the way. Even MySQL also. I mean, you can use techniques like Galera, for example, to be able to do MultiDC synchronous replication. But Nexus is another way that you can, achieve the same thing, right? And by the way, DKV also uses Nexus through and through to be able to do synchronous replication of its key space. Okay, and this is also an open source project at that repository. Next slide, please. Right. So this particular diagram explains a bit detail in terms of how does consensus writes work. Okay, so essentially on the right side you have a client which is sitting somewhere in the internet, okay, away from your data center somewhere. It is issuing a write, and that write is going to be handled by a designated node called leader. So the leader, there is a as part of the Raft lingo, that terminology comes from that Raft terminology, Raft domain. So that's a leader node. Leader node accepts your writes, and it is going to orchestrate that write across the multiple followers. All right. So it is going to basically forward that request, okay, to multiple followers, and it will wait for acknowledgements until the quorum number of nodes respond back to the leader as the acknowledgement, as the write has succeeded, and only then it is going to commit that write. So in a way, you could think about that as a two-phase commit run over a quorum of nodes, okay? And all of that orchestration is governed by the Raft protocol, okay? And it is this capability that is exposed by Nexus to the users, okay? So this is about consensus, right? So the word consensus comes from the fact that the leader is contacting a certain number of nodes with positive acknowledgements of that write, okay? So that minimum set is the quorum set, okay? And once there is agreement about that particular write, only then the leader will proceed with that write, okay? So that is consensus, right? And we use this very heavily in our DKV approach. Okay, next slide, please. Right. So this is another aspect that I wanted to touch upon, which is sharding, because obviously when data grows, right, both organic as well as inorganic growth events, data cannot basically be put up in a single node or a single box, so it has to spill over. Sharding is one way we could basically do this. In DKV, there is support for sharding, but it is client-side sharding for the time being. So in other words, the Java client as well as the Golang client will basically have a hash-based partitioner for your keys. So when you program when you integrate with that client, you can provide an implementation of this hash-based partitioner, which is going to choose a particular shard based on the keys hash value. And you can also plug in a custom partitioner as well to distribute your keys across the DKV nodes. Now, this sharding also makes use of Envoy to be able to route the requests to the appropriate shard master. Okay, and the routing is actually handled via Envoy. Right. So all of that is transparent. Envoy, gives us the ability to be transparent there. Right. So that's the sharding feature. Next slide, please, Kinshuk. Right. So from here onwards, I will hand over to Kinshuk, who will walk you through the rest of the slides. Thank you.
Thank you, Kalyan, for the intro. So I will continue on the API set of that are exposed by DKV. So essentially, DKV exposes the standard CRUD operations that anybody would need to operate on any KV store. So the standard put, get, and delete operations are there, and along with their batch counterparts like multi-get and multi-put. Also, all of these operations where we do a multi-put or a put, this native we do support like a native TTL on this, so each key operations can have this. Uh, Now, if you see the get signature, this is something different from what you would essentially see from a standard get operation. Like whether with a key, there is also a consistency parameter, right? As Kalyan previously mentioned, that we offer tunable consistency. So, and this tunable consistency is at the key level. So essentially, when you are requesting for a key, you could request what kind of consistency do you require with that particular key. Now coming to the next part is the cache operation. So this is the atomic read, modify, write operations, which you could use to do atomic changes of data. You can think of, let's say, implementing, let's say, auto incrementers, like you could increment by 1 or by n numbers, or do decrement operations. So all of those operations which are atomic in nature are possible by the cache operators. Apart from these, we do also offer scans. Now, these scans could be either prefix-based scans or even a full table scan. And this is up to the end users who want to use these operations on their shards. Coming to say this, all of these operations are on particular shard, and all of these APIs automatically gets routed to their appropriate shards based on the key that is being passed. On the administrative side of the things, we offer the backup, restore, and the cluster management APIs, which allows an administrator to manage the cluster. Next, coming to the read section. So as I said earlier, right, the key get signature is essentially a key and the consistency level, right? So we offer essentially three kind of consistency level, that is the linearizable and the sequential and the eventual. So linearizable, to explain linearizable, you can think of that this is kind of the strongly consistent kind of writes, where essentially a good example would be, let's say, when you have a single node database sort of things, wherein all of your reads and writes are happening on a single node. So that allows you to have kind of linearizable writes without any issues. Now that changes when you have a distributed kind of a multi-master kind of things, and that is what is offered in DKV. Coming to the sequential, right? Now, sequential consistency means that by definition by Jepsen is that all of the writes must be globally ordered. So to give you a simple example is that, let's say there are 4 processes which are doing write and read operations. So P1 and P2, let's say they are operating on a key A and B, and they are making a write operations to A as 1 and B 2. Now, the readers of this key space should exactly see the sequence, the change in exact order. So essentially P3 and P4 should see it in exact order. And as you can see that when it is going to read at B, so essentially they could, let's say B operation gets applied first, so both of them read B with the correct value. Now in the next time when, let's say, the P3, it might not get the data, and that is perfectly okay, wherein the P4 gets the right value, and when P3 will try to get it again the next attempt, and it will get. So essentially, if you see over the timeline view, they exactly see the writes in the order that has happened, and everybody gets the exact same view. So this is what sequential consistency means. And for us in DKV, given that all of our writes happen in an order, and given the RAF quorum, so essentially all of the writes happen through the leader. So the client, when requesting, is always going to read, can request any of the nodes, whether it's a leader node or a follower node, for the reads, and the sequential consistency can get served from any of them. For the linearizable, the client could also contact the leader. But now, let's say if you want to scale on the linearizable reads, what would happen is this will get bottlenecked on the leader. So what also DKV offers is something called as lease-based reads. Now, this allows the client also to contact the follower to get linearizable read, and the follower and this RAF quorum has a lease on who is the leader and what are the rights, and the follower would do a status check of what is this current status and compare it with the leader. And the moment it finds a match, it would just serve out the data locally, and the read will be still with the same consistency, and the reads now can get distributed across all of the quorum members. Coming to the eventual reads, this is what an eventual read can look like. So essentially, we have is also a lot of read replicas to scale up our reads, right? And this does is what it does is an async replication, and it replicates from any of the followers, and it is going to have that CDC mechanism to replicate through from the follower. And with this, what the client can actually is, client could actually contact any of the nodes to get a read of an eventual consistency, and that would give it that get that read. To the read replicas. As we were speaking, right, this is similar to a master slave topology, right? If you see, just like a master slave topology, and this is using a simple CDC mechanism, changes from this follower. But what also you see is other side, another topology where the leader is making the making a quorum right to the follower. So this on the right hand side, you see that it is the quorum that is happening, and the replicas are using a separate topology of a CDC mechanism to replicate asynchronously from the followers. And the discovery manager is there, and everybody has reporting the status. So discovery manager also knows the cluster members. Now, one of the with the standard problem that the master self topology is that what happens if the goes down. So let's say this follower one goes down. So then there is an issue that this replica will be lagging. To solve that issue, what we did is say that, okay, given that our read replica could also the discovery manager saying that give me who followers this kind of chart, and what it would switch over. The replicas will be constantly in sync with the followers, and even if one of them goes down, it will be able to transfer to another follower. And what this allows is that this allows a very automated way to manage the cluster without any manual intervention required. Coming to the discovery manager. So the discovery manager is runs the exactly same runtime as the. So it is when we launch this with discovery, underlying as a storage engine uses ROSDB for the storage engine, and exposes some administrative APIs which all of the other members report status. This also you have replication to have that data replicated across its member, and we will see how this is hosted. This is usually co-hosted along the DKV so that it doesn't require any other compute power or storage to be separately hosted. The main task of the discovery manager is to track the cluster members, so it does a periodic health check to all of the cluster members, and also in the reverse way, each of the node also periodically updates their status to this discovery manager. That way, what happens is the information in discovery manager is always up to date. Even if a node is going down, before the node shuts down, it would send that information to discovery manager that it is shutting down, and what would happen is that information would get propagated throughout the entire cluster, and wherever any switch is required, that can also happen. That helps with the coming to the network abstraction. So as Kalyan said earlier, like we have always this envoy sidecar that allows us to abstract out the network. So what happens is the app servers never directly talks to any of the nodes. It always talks via the envoy. So envoy acts as the proxy for all of the requests. And what happens, what topology we have is that we have a component called DKV who speaks the XDS protocol, which the envoy understands. And by this, what we do is we push the entire network topology of the current status to envoy. So this allows envoy to always route the request to the active DKV nodes. Even if, let's say, a node is going down, it will automatically know that that node is going down, and on the next request, it will automatically route to other active nodes. And what this helps is it completely abstracts the entire network changes from the client. So any maintenance, any node going down or node coming up, adding of a new node is completely seamless, and the app never needs to do any restart. Coming to the scalability point of view. So for DKV, increasing capacity is very easy. So adding the read-only async slips directly allows us to scale horizontally as much of read as we want. And also, as we discussed, the failover handling is really automated because envoy takes care of that. Now we did an YCSB benchmark on our reads, and on the right-hand side, you see that we almost peaked around 1 million QPS, and this is from just a 10 in-memory replica nodes of 64 GB memory, and with a very low P99 of somewhere around sub 100 tenths of milliseconds only. Now to summarize that, so what DKV is best suited for is high availability reads. When you require your system to be very available for reads always, so that is where DKV is where we say it is best suited for. And we will you can, as we said, that whenever, even if there is a write, let's say even if your quorum member, you lose your quorum members for let's say even a massive outage, you will be able to still serve the reads because from your async slaves with eventual consistency. The writes are always strongly consistent and durable writes. The quorum ensures that even if you lose few nodes and you still have a majority, you have always consistent durable writes. DKV is cloud native, it's elastic, it's auto discoverability, low maintenance, and takes care of all of the network abstraction, manageability of things directly into its own, the way it has been built. Another thing is where this is where we propose and we are using is all over where you require cross-region multi-DC deployments, and that is the best place, right? Because when Flipkart grew from a single DC to a multi-DC, things within a particular DC was much easier. But with multi-DC, when you want to have synchronization between DCs, we want to have consistent view. That is where we see a consensus-based KV store bridging that gap and becoming the best option to available. DKV, as we discussed, this is completely open source. This is distributed as with Apache 2.0 license and available on the Flipkart incubator GitHub. Some of the upcoming features that we have is the access controls. So access controls on the APIs, on the secure network access. So securing the network between each of the DKV nodes. so that the communications are also secure. Another upcoming feature is what is the server-side sharding. Today we offer client-side sharding, but one of the upcoming features that is planned is that server-side sharding, which would allow us also to do automatic resharding of the data when a shard goes down, or let's say there is a one of the shard has more data, so that would allow us to balance the shards. Cross-shard transactions. Today, any of the transactions that are supported are within a single shard. So with the server-side sharding, we would also be able to do the cross-shard transactions. Administrative interface, UI interface is something also that is coming up, and also Prometheus support is something that is coming up. Thank you.